Bonjour, mon nom est Raed El Ferjani. Je suis agent d'échange de connaissances et de mobilisation autochtone au Centre de foresterie des Laurentides et j'animerai ce webinaire. Avant de laisser la parole à mon collègue Armand Séguin, directeur de recherche au Centre de foresterie des Laurentides, qui va présenter le conférencier, voici quelques consignes d'usage. Au bas de votre écran, veuillez fermer votre caméra si ce n'est déjà fait. Pour activer la boîte de chat, cliquez sur l'icône bulle en bas à droite. La période de questions se fera à la fin de la présentation. Finalement, j'aimerais mentionner que le webinaire est enregistré. Je laisse maintenant la parole à Armand.
Bonjour tout le monde, mon nom est Armand Séguin. Je suis directeur intérimaire de la division de biologie forestière au Centre de foresterie des Laurentides. Alors, bienvenue à ce troisième webinaire de la 38e saison des colloques du SCF-CFL. Donc, aujourd'hui, la conférence s'intitule The Forest Water Nexus in a Changing Environment, 40 plus years of insight from the Turkey Lakes Watershed. Donc, c'est avec plaisir que je vous présente le conférencier, Monsieur Jason Leach. It's a pleasure to introduce our guest speaker, Jason Leach. Jason est hydrologue forestier au Centre de foresterie des Grands Lacs à Sault-Sainte-Marie en Ontario. Il a obtenu son doctorat de l'Université de Colombie-Britannique et il a travaillé sur divers projets d'hydrologie, tant au Canada, aux États-Unis qu'en Suède. Donc, ses recherches visent à comprendre comment les cours d'eau et leurs bassins versants forestiers réagissent au changement climatique tels que l'exploitation forestière, les forêts, les feux de forêt et les changements climatiques. Donc, je vous souhaite un bon colloque et je laisse maintenant la parole à Monsieur Jason Leach.
OK, bonjour. Merci beaucoup de m'avoir invité ici aujourd'hui. Je pensais essayer de faire cette présentation en français, mais je ne voulais pas vous faire souffrir. So instead, I'm going to do it in English. And you might still suffer through this, but at least I should be able to get more of the words pronounced correctly. Not necessarily all of them, but I'll still get most, I think, a bit better than if I were to do this in French. But as mentioned, my name is Jason Leach, and I'm a research scientist in forest hydrology at the Great Lakes Forestry Center. When I was asked to give this presentation as part of this series back in the summer, I believe, I had to provide a title, and I needed a title that was generic enough so that I could figure out what I was going to talk about, but specific enough that it at least sounded somewhat interesting. So the title you see here today, the Forest Water Nexus in a Changing Environment, 40 plus years of insights from the Turkey Lakes Watershed. We will touch on some of this, but we'll also focus on a few specific projects to hopefully highlight the broader importance of forest water processes and long-term ecosystem research sites for really informing sustainable forest management. So before I get into it, I'd like to thank a number of collaborators who have contributed to the work you'll see today. They are Daniel Hudson, Jamie Broad, Kara Webster, and Eric Emelson, our colleagues here at Great Lakes Forestry Center, who have all contributed in some way to the presentation today. In addition, some of the more specific research was done in collaboration with Dan Moore at UBC. And then, of course, we often need money to do some of this work, and funding for these projects were provided by NSERC, as well as the SFM and cumulative effects programs here within the Canadian Forest Service. The Turkey Lakes Watershed, as well as where I live and work, is on the traditional territory of the Batchewana First Nation, and we thank them for accommodating these efforts. Finally, Turkey Lakes is built on the time and efforts of countless past and present research scientists, technicians, and directors. And we thank them for seeing the value and supporting long-term ecosystem research. So a theme I will return to throughout this presentation is really highlighting the value of long-term ecosystem research sites. So what do I mean by long-term ecosystem research sites? Well, these are lands that are often dedicated for ecosystem research with the purpose of really unraveling the principles and processes of ecological science, especially those processes occurring over long time frames that are also, subject to legacy influences or rare events. And these types of sites are often have a concentration of focused research efforts, especially field and on-the-ground data collection. and do require some investment of resources, both people and money. And it's because of, because sort of going out to the land and collecting data can cost money, these types of sites are often subject to funding challenges. And so for this reason, I think it's really important to highlight some of the key values these sites provide. And so first of all, these sites really enable us to empirically quantify ecological response to change at various timescales. And also because these sites involve extensive field measurements of various processes within an ecosystem, we are able to develop an understanding of complex ecosystem processes, again, over prolonged periods. And I think a really critical contribution of these sites is that they also provide core data to develop and test models. I think this is really important because sometimes we hear, well, why does intensively measuring a small 10 square kilometer watershed in Northern Ontario matter for the rest of Canada? And I would argue that certain ecosystem models that can be applied to larger spatial scales need really strong conceptual understanding and detailed data in order to ensure that these models are giving us the right answer for the right reasons. And really long-term ecosystem research sites really provide these data for robust model development and testing. So another key feature of these sites are that they really encourage collaboration and multidisciplinary research, since you often have a whole bunch of different groups working at the same location. And then finally, I think these types of sites also provide data and understanding at scales that are highly relevant to management. We often make management decisions at stand or watershed scales, and that is often the spatial scale that many of these sites operate at. So there's a legacy of long-term ecosystem research in Canada. In particular, there's a history of forest watershed studies throughout Canada, and that's going to be a theme that follows through my talk today. And you can see the map on the right there. It compiles all these sites, and over time we've had about 45 sort of forest ecosystem watershed studies in Canada. However, these sites have never been coordinated at a national level. And I think this lack of coordination has really led to differences in core measurements, which limit national scale syntheses. And I think most concerning is that we are losing these sites. So in 2007, only about 29 were still active. And currently there are maybe around 12 that are still in operation. And not only that, but I intentionally use active in quotes here because even if they are still operating on paper, for many of these sites, the ongoing measurements are really only a shadow of what they used to be or really need to be. The sites that is still going is the Turkey Lakes Watershed, and it's a long-term ecosystem research site primarily operated by the Canadian Forest Service with the involvement from ECCC or Environment and Climate Change Canada, DFO, and provincial and university partners. So Turkey Lakes is located near the eastern shores of Lake Superior, about an hour north of Sault Ste. Marie, where I'm located. It was established in 1979 to initially focus on ecosystem effects of acid rain. The initial study design was really focused on a whole ecosystem approach, and this idea of measuring as many of the ecosystem components as possible. And that has resulted in Turkey Lakes being one of the most integrated and interdisciplinary long-term ecological research sites in Canada. And as you'll see, I think that decision to focus on a whole ecosystem approach has really allowed the site to pivot and address a wide range of research questions through its existence. So I'll give you just a little taste of the site and infrastructure here. So the full watershed is about 10 square kilometers. We have a wide variety of ongoing measurements being made throughout the watershed, including meteorological, hydrologic, soil, and vegetation measurements. The top right picture there shows the main headquarters. The bottom right picture shows the main meteorological station. And as we'll discuss, not only are we approaching 45 years of data collected at the site, but there was also an experimental harvest done in the late 90s that provides really an amazing opportunity to look at longer-term effects of different silvicultural practices on ecosystem response. And so over the 45 years, the science done at the site has evolved. From that early focus on acid rain effects to looking at harvesting impacts, carbon dynamics, to more recent focus on nature-based solutions for drinking water supply, among a whole bunch of other things. There's over 500 publications now from Turkey Lakes, which include a real mix of long and short-term studies, as well as theoretical and applied work. Much of the work is site-based, obviously. However, data from Turkey Lakes often contributes to sort of national and international synthesis studies. And as I touched on earlier, there's a strong focus on empirical research, but the site has been used extensively for building and rigorously testing models as well. So let's get into some of the data. As mentioned, I'm a forest hydrologist, so you're going to see a real focus on hydrologic data in this talk. That's not to say that there's a lot of really interesting things from the more vegetation side and other aspects of the study. But we're going to focus on some of these data because that's what I like to look at and understand. So let's start and see how the climate has been changing at the site. So this figure shows annual air temperature deviations from a long-term mean. The individual points are annual values, and the thick line is the 5-year moving mean. And you can see that the first 15 years at the site were generally below average in terms of temperature. We had a warming period during the 2000s, and in the last decade or so, mean temperatures have dropped slightly. So we're really quite fortunate that there's a long-term weather station in Sault Ste. Marie, Michigan, just across the border that goes back to about 1930. And we can use this station to help put the last 45 years within a longer-term context. And from this figure, we can clearly see that there's been an overall warming trend over the last 100 years or so. And for the overlapping period, where we have data both at Turkey Lakes and the Sault, Michigan site, we see that both sites generally follow the same pattern, but there are some differences between the two sites, which I think really underscores the need for local on-site measurements of these variables. So that was air temperature. We can also look at long-term patterns in precipitation. In general, we see that in the 1980s to mid-90s was a relatively wet period. It was a bit drier from the late 90s until about 2010 or so. And in the last decade or so, we've returned to generally wetter conditions. So again, we can place these within a longer term context using the Sault, Michigan station. We don't necessarily see a strong trend like we did with air temperature, but it could be argued that we see more variability in recent decades compared to the earlier part of the record. For example, some of the years with the greatest and lowest precipitation amounts are occurring in more recent years. So we can also look at how these climate patterns influence something like streamflow at the site. And so these 4 graphs show different streamflow signatures for one of our monitored catchments over the last 40 years. So if we look at the figure in the top left, this shows our annual maximum flow, so our biggest flood day per year. We can see that after a bit of a increasing flood magnitude at the start of the record, we have generally seen an overall decline in maximum flows at the site. And what is interesting is that we see this decline in maximum flow, especially over the last 15 years, at the same time that we are seeing a general increase in mean annual flow, as shown in the top right. So this suggests that the precipitation distribution throughout the year is changing. I think this is further supported by the graph in the lower left, which shows the day of the year that the annual maximum flow is occurring. So for most years, the annual max flow occurs around, give or take, day 100, which in this part of the world, and similar to Quebec, it sort of is associated with snowmelt. So this is our big snowmelt-derived flood. However, some years you can see that the maximum flow happens in the fall, so around day 300, again, give or take. And these are often as the result of big autumn rain events. So it appears that this, maybe is starting to happen a bit more in recent years, which is sort of an interesting trend that we're sort of monitoring and keeping an eye on. So finally, the last figure in the bottom right shows the number of days without flow for this one stream in particular. And we can see that it generally follows the precipitation and air temperature patterns at the site, where we had wetter and colder conditions from around 1980 to the mid-90s, followed by drier and warmer conditions until about 2010. And then the last decade or so has been wetter. I mostly want to show this last graph, since in some jurisdictions, certain harvesting activities depend on whether a stream has permanent or temporary flow. And I think that what this graph does is highlight that this designation can be quite variable through time. So we could spend the next few hours going through a whole bunch of graphs like these, showing patterns in different ecosystem variables over the last 45 years. And that would be fun, and I think it could be interesting. But what I want to do is take the next chunk of time and really take a deep dive into one specific variable. And I think this is a measurement that I'm almost certain when the team first established Turkey Lakes, they had no expectation that there would be some interesting insights revealed on climate and forestry effects 45 years later. So I hope with this example that I'll be able to show you that there's a ton of sort of value and surprises that come from making comprehensive long-term ecosystem research or measurements. And so that mystery variable is stream temperature. So why do we care about stream temperature? Well, stream temperature has been referred to as the master variable of aquatic ecosystems, since it controls a whole slew of biological, chemical, and physical processes occurring in the stream environment. There are concerns that climate and land cover changes, such as harvesting, wildfire, urbanization, are altering our stream thermal regimes. And these changes may be having a negative impact on fish, in particularly cold water species, such as trout and salmon. And so these fish can have significant social, cultural, and economic value. And because of this, there's a need to, I think, really understand how these environmental changes are altering stream temperature, really to inform effective management approaches to protect aquatic ecosystems and the fish that depend on them. So from a forestry perspective, there's been considerable research on this topic over the past few decades, and most of this work has really focused on summer periods. And for good reason, since summer is often the time we see the highest stream temperatures and potential for temperatures to exceed thermal tolerances for fish. As you can see, documented stream response to forest harvesting has shown quite a range, even from decreases in stream temperature to post-harvest increases of up to 12 degrees Celsius in some cases. Part of this variability is due to these studies occurring across different landscapes that vary in terms of their climate, forest types, and geology. In addition, forest harvesting approaches have varied across these studies in terms of their harvesting approaches or harvesting types, extent of harvest, and the types of riparian vegetation buffers applied, or in some cases lack thereof. So since forest harvesting can have a substantial influence on stream temperature, there's been attention in the media about how forest harvesting is having a detrimental effect on fish, such as the article on the left. Since forest management can affect streams and fish, and there's also an opportunity, I think there's also an opportunity to use our understanding of forest management to help augment and protect fish, especially under a warming climate. So for example, their article on the right covers some efforts from Scotland where reestablishing forests is viewed as really a key opportunity to improve salmon habitat in that part of the world. So applying these kinds of management interventions to sustain healthy aquatic ecosystems, I think really depends on a good scientific understanding of how these systems work. So this little cartoon here shows the key energy exchange processes acting on a stream. And we can broadly classify these energy exchange processes as those occurring at the stream-air interface, the stream bed interface, and finally hydrologic fluxes. And so for the stream-air interface, incoming solar radiation is often the most important energy input to streams. This is especially the case following harvesting when riparian vegetation cover can be removed or reduced. Other energy fluxes at the stream surface include incoming long-wave radiation from the atmosphere, from the canopy, from terrain, as well as outgoing radiation emitted from the stream. We also have the turbulent energy fluxes, which are comprised of the latent sensible heat fluxes. And then at the stream bed, we have bed heat conduction, energy added through friction. And then finally, the darker arrows highlight the various hydrologic fluxes. So that is water exchanges that add and remove heat. So for example, we can have a tributary inflow or groundwater inflows and outflows. All these sorts of water exchanges also, as I mentioned, carry with them heat and exchange heat with the stream. We can also have an energy flux associated with hyporheic exchange. And so hyporheic exchange is water that originates as stream water. It flows through the stream bed where its temperature can change since it mixes with groundwater and other energy and is influenced by that heat conduction. And then that water in the stream bed reemerges in the stream, often at a different temperature. So as mentioned, when thinking about forest harvesting impacts on stream temperature processes, really most of our concern is around increased solar radiation reaching the stream due to either full or partial removal of riparian trees. And a lot of our provincial regulations reflect this understanding around the role of riparian vegetation and solar radiation. So for example, I'm showing diagrams from the Ontario guidelines on the left and BC guidelines on the right. And in both cases, these guidelines really focus on riparian forest management for mitigating potential changes to stream temperature due to harvesting. And in some correspondence with some folks in Quebec, I believe this use of riparian buffers also has a long history there as well. So after this kind of somewhat lengthy background, what we're going to do today is use, as I mentioned, some accidental stream temperature measurements made at Turkey Lakes over the past 4 decades to answer the following 3 questions. So how are forested headwater thermal regimes changing in response to climate change? What is the stream temperature response to different harvesting approaches in a temperate hardwood forest? And finally, do stream temperature responses to harvesting in headwaters propagate downstream? So we're going to start with the first question: how are forested headwater thermal regimes changing in response to climate change? And the work that you're going to see here was really led by Daniel Hudson here at Great Lakes Forestry Center. So for this analysis, we're going to focus on data collected at 5 headwater catchments within Turkey Lakes, shown here. These are catchments that have not had any sort of harvesting done on them in the last at least 40 or 50 years, and even beyond that. So since about 1981, whenever a technician goes and visits some of these sites to collect a water sample, the technician puts a thermometer in the stream and records the temperature in a field book. Super simple, but has been done over and over and over again through the existence of the site. And so what happens is, if you do this often enough and over the years, you start to build a fairly good characterization of the thermal regime of these streams from these spot measurements. And what we see here are the individual temperature measurements for those 5 streams. And you can obviously see the sort of seasonal cycles emerge from these data with temperatures around 0 during the winter. Many of these streams freeze, and highest temperatures occurring during the summer. So we can take these data and start to compute some mean annual stream temperatures and look at long-term trends. And what we see is maybe a small general increase in temperature over the years for most of the sites, but it's not a very compelling or strong signal. However, if we look at seasonal patterns, a bit more of a story emerges. Winter temperatures seem to be declining. We are getting fairly clear warming patterns during spring. Summers, although highly variable from year to year, don't show any sort of, or don't show a real clear long-term trend. And then finally, fall is maybe showing a slight increasing trend, but it's not overly strong. In terms of the winter and spring trends, we think what might be going on here is really being driven by warmer winters with more midwinter melt events and declining snowpacks. So the midwinter melt events would contribute to cooler winter stream temperatures through sort of that meltwater, that cold meltwater entering the stream and cooling things down. And then the smaller snowpacks would mean less snow influence in spring, especially on the spring stream temperatures, and therefore a greater potential for stream warming during that period from the sun. So if we compare our findings with other studies that have looked at long-term stream temperature trends for forested watersheds, we see a couple interesting contrasts. So one example, and part in the busy figure there from Isaac et al., they're a team of US Forest Service scientists, and there's a lot going on there, but in generally, they found that the greatest stream temperature increases for their sites are occurring during summer. And this is a fairly typical result for most other studies too that have looked at these sorts of trends. And as I mentioned, this seems to contrast directly with what we found at Turkey Lakes, where summer wasn't showing any clear increasing trend. So there may be a few reasons for this, but most of this other research that's out there is really from larger streams and rivers than those studied at Turkey Lakes. So globally, we have very little long-term data from small, very small streams like we monitor at Turkey Lakes. So it's quite a unique aspect of this study. And I think our findings perhaps suggest that the thermal regimes of these small headwater streams might be responding differently to climate change than larger rivers. And I would argue that this is quite important to know, since approaches to conserve cold water habitat in a warming climate may need to differ depending on the size of the stream that you're looking at. So for this first little research question, as mentioned, we find that most of the warming occurred during spring and there was no clear trend in summer. I've also provided some estimates of the trends here in terms of temperature change per decade. And you can kind of quickly make note of these because these will be important when we start comparing climate change effects to the effects from harvesting. Which leads us into the second question that we'll address today, and what is the stream temperature response to different harvesting approaches in a temperate hardwood forest? So as I mentioned, a harvesting experiment was conducted in 1997 at Turkey Lakes, where 3 of the catchments were harvested using clear-cut selection and shelterwood approaches. And you can see these on the map shown here. So I'll talk a little bit more about these harvesting approaches in a second, but there was also a number of other catchments, which some I've shown you already, that were retained as references, and you can see 2 of them shown here on the map. So again, we use spot temperature measurements in this study collected as part of the routine monitoring program at the site. And we really focused on leaf-on June to September stream temperature response to harvesting. So I didn't really get into this earlier, but obviously spot temperatures have a number of limitations. And I don't necessarily have a ton of time to get into that now, but just suffice to say that we were able to control for many of these in our analysis. And if anybody's interested, we can talk about this a little bit more. Sorry, I just got a weird notification coming up there. Okay. Where was I? Yeah, I think a really important or a real key strength of these data was that we had 16 and 23 years of pre and post harvest measurements. This is almost unheard of in any sort of harvesting stream temperature study. And what the value of that is, we're really able to capture a wide range of hydroclimatic conditions, both in the pre and post harvest periods, but then also we can sort of look at recovery or potential recovery at these sites. So I just want to talk real briefly about the different harvesting treatments used in this study. Some of the catchments were not harvested, and these are obviously our reference sites. One catchment, C31, was clear cut, which involved removing any tree with a DBH over 20 centimeters. Some smaller trees were left on site, and this sort of resulted in about 22% overstory volume left post-harvest. I should note that clear cutting is not a recommended harvesting approach in these types of forests, but was really included as an experimental treatment to really push the system as far as possible. Selection harvest, which is the most common approach to logging used in this region, involves removing individual trees, which ultimately creates an uneven age system. And in that case, about 64% of the overstory volume was left post-harvest. And then finally, shelterwood harvest, which involves removing around 50% of the mature trees to create an even age system, also results in a very similar amount of remaining overstory volume compared to the selection harvest. So this figure here shows the individual spot water temperature measurements made at the 3 harvested and 2 reference catchments. The vertical gray band shows the period of harvest. The key things to draw from this graph is, again, that seeing the seasonal variability in stream temperature, and also to get a sense of the number of measurements made over the study period, and sort of an appreciation in some ways of how often these streams have been visited over the 40 years. So just a tiny bit on methodology here. So we used a BACI design, or before-after control impact design, where the reference and treatment catchments are monitored for a period prior to harvesting to establish relationships. And then deviations from those relationships in the post-harvest period should be attributable to a harvesting effect. We used a 3-year moving windows to account for, in some cases, relatively small sample sizes, particularly during the summer, while still being able to capture these temporal changes in harvesting response. We also used models fit to reference catchments, to 2 reference catchments, and this was really intended to sort of check the methodology, and I'll show what I mean by that in a second. Before we get into the stream temperature response, I just want to talk a bit about the post-harvest period. So this figure shows leaf area index values for the reference clearcut and shelterwood sites following harvesting in 1997. So these values give you an idea of the canopy cover of the forest. So the top graph shows only the overstory or mature trees, while the bottom graph shows both understory and overstory together. And what you can see is that the shelterwood leaf area index is not that much different from the reference during the post-harvest period, whereas the clearcut clearly shows a decrease in canopy cover, but that we see recovery to harvest conditions after about 5 to 7 years post-harvest. So these LAI data weren't collected at the selection harvest, I should note that, but there's been other measures of canopy cover that have shown very similar characteristics between the shelter and selection harvest sites. Oops. Another important aspect of these catchments is that most of these small streams dry up for varying periods during the summer. So the figure on the left shows that except for C34, the shelterwood harvest, and which also happens to be the largest watershed in the study, most of these small streams dry up during the summer period. And as you'll see, this is important and something we will revisit shortly. Another hydrologic context I want to provide you is how the summer stream flow responded to harvesting. So this figure shows the difference between observed and predicted June to September runoff from C33. So this is the selection harvest catchment. For both the pre-harvest period, so that's left of the dashed line, and the post-harvest period, right, and this is right of the dashed line. So if there was a strong harvesting effect on stream flow for this summer period, we would expect to see large and persistent positive values in the post-harvest period. So interestingly, for the first decade or so, we don't see this, and the values are well within the range of the pre-harvest, what we see in the pre-harvest period. So so that's interesting. But around 2010 or so, we start to see consistently positive values, perhaps suggesting that there was a delayed harvesting response in summer stream flow at this catchment. And that really begs the question, well, why? Why is that? Well, what we think may be happening is that first decade or so following harvesting was characterized by relatively dry and warm conditions. So we think that there was limited excess water for runoff following harvesting because it was so dry. Essentially, the remaining trees in the catchment were able to snatch it up. However, starting around 2010, we shifted into a wetter period, and we started to see possible stream flow increases associated with harvesting that may have lasted for a few years, as we see here, as indicated by these mostly positive values from about 2010 to 2020. We'll revisit the potential implications for the stream flow harvesting response on stream temperature shortly, but just wanted to give you a sense of what may be happening at the site hydrologically in response to the harvesting. So this slide here shows scatter plots of pre-harvest spot temperature measurements for the three harvested catchments, as well as C35 in the bottom right corner. This is the reference catchment, and they're all plotted against C32, the other reference catchment. And what you see, this is, I think I mentioned these are the pre-harvest spot measurements, and what you see is that most of the pre-harvest relationships are fairly good. Although the reference versus reference relationship in the bottom right corner is a little more noisy. And now what we can do is we can plot the post-harvest measurements on the same graph. And for all the sites except for C31, the clear-cut site, the post-harvest points generally fall within the pre-harvest range, suggesting no harvesting effect. For the clear-cut site, however, we do see for the years immediately following harvesting, a trend for those points to plot a little higher than the pre-harvest relationship, I think suggesting that we're seeing a harvesting response of increased stream temperature of that catchment. And we can look at these data in another way on the next slide here. So this plot shows the estimated stream temperature response for 3-year moving windows at the harvested catchments. And again, as well as a reference catchment used to check the methodology. That's the bottom graph there. So the vertical gray band indicates the time of harvest again in 1997. And so for the pre-harvest period, as well as the reference catchment comparison, what we're really looking for are those estimates to straddle zero. If the estimates deviate from zero, that suggests a detectable difference in stream temperature for that 3-year period compared to the pre-harvest relationship. So I really want to focus on sort of 3 key results here. And first, only the clear cut showed a stream temperature response to harvesting. And although the response persisted for 5 to 7 years, it was less than 2-degree increase. This is pretty low compared to most other clear cut studies, which see temperature increases of up to about 12 degrees, as I'd shown in that earlier slide. And we suspect that the muted response is likely due to these streams often drying up during the late summer, as shown in the picture here. And it's essentially, if you don't have water in your stream, it really can't be heated. So second, the timing of recovery at the clear cut, as well as the lack of response for the selection and shelterwood streams, I think are really consistent with observed forest canopy dynamics, which I have kind of shown you in the previous slide and show here again. And we found that the selection shelterwood harvest sites didn't see much change in leaf area index following harvesting, and the clear-cut site returned to reference conditions within 5 to 7 years. And this is quite consistent with what we're seeing in the stream temperature response. And then finally, there appears to be kind of a small decrease in stream temperature that occurred about 11 years following harvesting. And what's interesting is, it's not big, but it's fairly persistent across all the harvested catchments, but we don't see that in the reference comparison. And what's interesting here is this seems to correspond with the delayed hydrologic response for these catchments that I showed you a little bit earlier. Again, since that initial decade following harvesting was relatively dry. And then, we don't. So I think what's happening here is that, again, those harvesting catchments didn't really show a strong increase in summer stream flow until about this sort of 10, 11 years after harvesting, once we entered a wetter period. And so we suspect that this increase in flow due to greater subsurface runoff with a recovered forest canopy may be driving this small cooling effect. So I just want to take a moment and highlight that we see some similar results to those studies. We see some similar results from Turkey Lakes with studies from other regions. So the graph on the left is from a study by Janish and colleagues that was conducted in the Pacific Northwest. Similar to our work, they found that short, intermittently flowing streams had a more muted stream temperature response to harvesting than longer streams with more permanent flow. So again, underscoring that these sort of small headwater streams can behave quite differently than our larger rivers and streams. The plot on the right is from a study in Japan by Aoun and colleagues. They found that stream temperature responses to harvesting were less during days with high flows than with low flows for a given amount of solar radiation. Although they couldn't conclusively say that stream flow increased following harvesting in their study, since they didn't really have that data available to make those to answer those questions, the patterns shown on this plot suggest that if stream flow increased, we would expect that increases in stream flow to help offset some of the stream temperature increases due to harvesting, which may be what we're seeing at Turkey Lakes as well in that sort of 10, 11 year post-harvest period. So the findings I just shared with you are again, as I mentioned, from small headwater catchments, and much of our understanding on stream temperature response to harvesting is from these types of systems, because they're relatively easy to use within a backy experimental design. But a major question around sort of stream temperature response to harvesting is whether effects propagate downstream, which brings us to our question number 3 that you see here. So fortunately, we have some data available at Turkey Lakes that allows us to explore this question. So the map I'm showing you here highlights the 3 harvested catchments. Stream temperature has also been collected at S4 and S5 as indicated on the maps. And these are locations along a creek called Norbert Creek. And all the harvested catchments drain into this section of reach. So we have measurements pre and post harvest made both upstream and downstream of the harvesting inflows. I want to note too that the harvested area makes up only about 7% of the total catchment draining into S5, and about 33% of the total area draining into that section between S4 and S5. And another important thing is that you'll see that S4 is immediately downstream of a lake outlet. This lake here, which if you really squint your eyes is how Turkey Lakes got its name, because supposedly this kind of looks like a turkey. Your mileage may vary on that interpretation. So anyway, this figure here shows estimated stream temperature response to harvesting at the S5 site. The line range is the 95% uncertainty intervals in the estimated harvesting response. And as you can see, almost all of them cross 0, suggesting that there isn't a clear downstream temperature response to harvesting. Now, we didn't see much of a response at the headwater catchments. Only the clear cut showed a clear harvesting signal. And also the harvested area isn't a huge amount of the total catchment area, so it's not that surprising that we don't see an effect downstream. And another reason we likely don't see an effect is that these receiving waters are quite a bit warmer than the headwater sites. We actually see a decrease in temperature as we move from S4 to the downstream location at S5. And as mentioned, the S4 drains a lake, and that lake essentially acts as a large solar panel during the summer and discharges water downstream, up to 30 degrees Celsius. So even if we had seen perhaps a larger harvesting response in the headwaters, and if more of the catchment had been harvested, it's potentially likely that we may not see a harvesting impact on Norbert Creek, since the stream temperature is already elevated due to this lake effect. I think in addition, so what this highlights, I think, is that these temporary streams, post-harvest stream flow changes, as well as, as the role of lakes, all highlight that the hydrologic context of these sort of settings can be really important for understanding harvesting effects on stream temperature. And just to leave you one other thing, like these small lakes are really common, especially throughout Canada's forested landscape. So this is an image from just north of Sault Ste. Marie, and we can see that this landscape is absolutely littered with small lakes. And I think something that we need to do a better job of, both from research and forest management perspectives, is how to think about the effects of forest change on water resources and aquatic ecosystems in these sorts of complex lake stream networks. Because historically, these sorts of systems, these lakes and streams, have been studied separately. That's been changing over the last decade or so, but I think there's still a lot more to do in this realm. So to wrap up, I'd like to sort of summarize some of the key messages from today. First, stream temperatures are increasing at Turkey Lakes, but the magnitude varies by season. Stream temperature increase due to clear cutting, but not selection or shelterwood harvest. And I think this suggests that these kinds of harvesting treatments can be, quote unquote, sustainable, at least from a stream temperature perspective, when applied in a similar way to what was done at Turkey Lakes. And also for context, summer temperatures appeared to increase by 1 to 2 degrees Celsius at the clear-cut streams. And this is about the same amount of increase that we see in the mean annual temperature of these streams over the course of the 40 years due to climate variability. So that provides you some context there. In our case, with this specific sort of case study, we didn't find any harvesting effects propagating downstream from the cut blocks. And then overall, these stream temperature trends and response, as I mentioned, were really strongly mediated by hydrology, both in terms of timing of flow, whether streams are temporary or ephemeral streams, as the stream flow response to harvesting, and also the presence of these small lakes. So I really hope this underscores the importance of understanding hydrologic context for interpreting aquatic ecosystem response to forest and climate change. And then finally, I also hope that this work highlights how long-term ecosystem research can provide hitherto unrecognized insights on sustainable forest management and cumulative effects. As mentioned, stream temperature was never a research objective of this site, but because of the dedication to the site and the detailed measurements, we are able to reveal through these studies some key insights on how forest ecosystems function. And this is just one small example, but there are countless others. So I just want to connect back to this idea of the value of long-term ecological research. As we see a lot of countries support and see the importance of this type of research, so much so that there are dedicated networks of these types of sites. These formal networks, I think, take all the benefits of having individual sites, such as collaboration, rigorous science, and contribution to model and synthesis work, and really magnifies those benefits. I think also these types of networks also really help resourcing and funding challenges in keeping these sorts of sites operating. And with that, I want to leave you with this final slide. So this map shows countries, those indicated in green, that have long-term ecosystem research networks, formal ones. And as you can see, there is one country that clearly stands out on this map for not being green. We can play a little quiz game and decide which one. But I'll let you contemplate that for a little bit. That's it for me. And I want to thank you very much for your time and attention. And if we have a little bit of time for questions, I'm more than happy to chat about some of this stuff. So thank you very much.
Merci beaucoup, Jason. Thank you very much. Pour ceux et celles qui se sont joints à nous, mon nom est Raed El Ferjani et j'animerai la période de questions. Avant de débuter, j'ai des messages d'intérêt et quelques règles d'usage à partager avec vous. Si vous le souhaitez, vous pouvez maintenant activer votre vidéo. Si vous désirez obtenir une attestation de formation continue, notamment en lien avec le règlement sur la formation continue obligatoire des ingénieurs forestiers du Québec, l'unique façon est de compléter l'attestation de participation avec le lien URL que vous trouverez dans le chat sous peu. Veuillez noter que le code d'activité est maintenant intégré dans le lien. Vous pouvez poser votre question dans la langue officielle de votre choix. Et il y a deux façons de le faire, verbalement en cliquant à droite de votre nom dans la liste de participants et sélectionner l'icône main levée. Lorsque je vous nommerai, vous n'aurez qu'à enlever votre mode sourdine en cliquant sur l'icône micro. Après avoir posé votre question, s'il vous plaît, vous remettre en mode sourdine. Nous souhaitons avoir une question à la fois, autant pour donner la chance aux conférenciers de bien répondre à votre question et de laisser la chance à tous de poser leurs questions. Si vous préférez poser votre question par écrit, utilisez la boîte du chat, sélectionnez l'icône en forme de bulle en bas à droite pour l'activer si ce n'est pas déjà fait. nous vous demandons de vous identifier clairement en donnant votre nom et l'organisation que vous représentez. Donc, la période des questions est maintenant commencée. Jason peut avoir vos questions orales ou écrites.
I think, Sylvain, you have your hand up. Maybe I don't know if you want me to orchestrate that, but nice to see a familiar face. So
yes,
thanks for tuning in.
Hi, Jason. How are you?
I'm doing well.
Good. I had a question about the seasonal variation of the temperature you've shown in Turkey Lakes. This is super interesting to see that winter temperature are going down and spring temperature are going up, while other seasons are not affected that much. Could it be related to the fact that the span of each season is kind of changing? So if you're using in those graphs always the same dates for the beginning of winter and end of winter and start of spring, you know, but those dates might be changing. And do you think that changing the span of what is now the new length of each season can have an effect on the results you're getting?
Yeah, that's a really interesting question. Before I get into that, I just want to say I that cheese that you gave me this summer, I think about it every single day. This is the best tasting thing I've ever had in my life. Anyway, yeah, so okay, so that's a very interesting question. I think so that my initial thought is that there could be some sort of circular, you know, classifying a season. How do we classify a season? And if that season's changing and we reclassify that, there may be sort of, you know, some perhaps circular reasoning in detecting a change for a given period of time, kind of thing. So, so I'd have to think about that a little bit more, but I think you're if you sort of look at it through a fixed window through time, I think you're absolutely spot on. I think what's happening under that's underpinning those trends that we're seeing are you know, are lengthening of certain seasons, you know, by their definition, however we want to define them, whether it's sort of like, you know, the end of you know, the loss of the snowpack being the, you know, the end of winter kind of thing, or these sorts of things. So yeah, I think that's what's happening and underpinning, like, you know, some of these trends that we're seeing. And I don't know, do you, like, maybe throw this back at you, like, is there a good example of you know, of people who have sort of taken a dynamic classification of seasons and use that to sort of look at these sorts of trend analyses? Or yeah. Oh,
Yes, thank you, Hyde. Because I cannot start back my
oh, sure, yeah.
The microphone. So we've seen, from what I understand, in Forêt-Montmorency and other places too, where climate, for example, the Atlas hydroclimatique du Québec, where they used climate change and tested it in spring flow through hydrological modeling for numerous rivers in Quebec. There is definitely a change in spring freshet and in period where spring flows are happening. So this change in the seasonal pattern of temperature is affecting also streams. So I don't think it gives a bad impression of the results you presented.
No.
The only thing is that it might be, for example, that during winter time, in your winter period frame you're using, there might be more spring freshets where cold water is going on, is flowing, included in this one. And since the water is cold at that period, it's not getting cold temperature in the spring period. It's giving it to the winter period. So this is kind of tricky, because if you...
Oh, we've lost your mic again. But anyway, I take your point exactly. Yeah, we did. So that's a really good point. So we did look into that a little bit, and fortunately, because we have the flow data to sort of match with these patterns and whatnot, and what seemed to be happening, at least in this case, I don't think there was so much that timing of freshet was sort of overlapping those seasonal definitions. It really seems to be we're having this higher frequency of midwinter melt events, and that seems to be, so we do see an increase in a small but a general increase in winter, quote unquote, winter flows at the site. That now I'm kind of curious. I wanted to go double check this, but I'm pretty sure we looked into this. That isn't attributed to the timing of the freshet, but is attributed to just these warm periods that we get, driving a lot of snow melt midwinter, and seeing these midwinter temporary increases in flow, kind of thing. But yeah, fantastic question for sure. Yeah, something to think about.
Can I go for a second question, right?
Sure.
Okay, good.
Sure.
I'll be a devil's advocate here. Aren't you scared of showing long-term studies results showing that, yeah, but harvesting is not showing any very interesting results? We could just don't care anymore, because selective cutting and partial cutting doesn't have any effect on spring on temperature. So for your bosses, not mine, but administrators of founding, those who are responsible of founding those long-term studies, are just scratching their head and saying, yeah, 40 years of money invested in just getting that type of results. Why should we continue? So I'm just asking you, how can you convince decision makers to continue provide money to those big time and money consuming sites? Because I'm in charge of one of those types of sites, and this is an issue we always have to deal with. So I need arguments. Please help me.
Yeah. Well, so first off, this is just one little slice of results that come out of this site, right? So this is just the stream temperature story. This is, and I think if anything, this is an argument for the value of these sites, because as I mentioned, at no point in the design of this study, even the harvesting experiment, was there, I don't think there was ever a discussion around, yeah, let's look at stream temperature. It was just really an accidental measurement made with a focus on, in particular, the water quality measurements that were made. And so this, to me, this entire component of the study is complete added value, accidental added value, right? And whatnot. Now, yeah, absolutely. From a stream temperature perspective, for this sort of study site, for this sort of harvesting treatment, these sort of comparison, we don't see a strong response. And I think that, and I think that's really important to know. And I would never hide that to, thing. On the flip side, if you look at some of the chemistry results, and my colleague Kara Webster has published some of this work recently, something like DOC, so carbon, a high profile sort of topic right now, especially aquatic carbon. We still see harvesting effects from that. Now 25 years post harvest, there are still elevated export of carbon from these watersheds. So so in one breath, one variable we see these sorts of dynamics. In another variable, that we see the value of continuing and looking at these sort of long-term effects. I think the carbon one is particularly interesting because it didn't really show a response in the first few years. And most studies only focus on the first few years post-harvest. And you would come up with very, very different conclusions had this study been stopped 5 years after harvesting compared to now 25 years plus after harvesting. These are very different conclusions that you would come to in terms of that. Arguably, same with the stream temperature. You would, if the study would stop 5 years after harvesting, you'd say, well, the clear cut creates elevated temperature. We don't know when it recovers. In this case, we have some evidence that we can see a recovery in these sorts of parameters. So anyway, yeah, it would be great to be friends with. Well, I probably wouldn't be great to be friends with Elon Musk, but it would, on some level, it would be fantastic to have some extremely rich benefactor who could, and just keep some of these sites alive. But yeah. Anyway.
Merci beaucoup, Sylvain. On a une question de David.
Great talk, Jason. I was just wondering about the clear-cut treatment. If you had some buffer strips, or if the streams were too small for that. And I think in Quebec, and the experts around the table can correct me, but it's mostly the buffer strip is to prevent trampling, and it's not necessarily to get shade on the streams. But what is your take on that?
Yeah, so that's a great question about the riparian treatments for these sites. So these are very small streams, and by Ontario standards don't necessarily require a buffer strip. There is restricted access for harvesting equipment in about 3 meters from the stream. They are allowed to go in, and this is what happened at the Turkey Lake site. They are allowed to go in and extract trees out of that 3 meter buffer, but driving any machinery into is not allowed. That being said, I assume, David, you've been to Turkey Lakes before, and you know the rugged terrain and whatnot. So especially in some of those stream valleys or channels, it's just really hard to access the trees in those sites. So there's almost a natural buffer is formed just due to inaccessibility. Yeah, so that's the case, and there has been some sort of densiometer measurements done by Dave Kurtzweiser's group at the time that sort of looked at stream measurements of sort of canopy reduction through these different harvesting treatment, and they match up quite nicely with those LAI data that I showed earlier. That is more from the sort of the terrestrial part of the catchment measurement. So we think that's a decent sort of proxy for that sort of stuff. And then to your question about sort of the Quebec regulations, I actually reached out to Sylvain Jutra a little bit earlier, just to sort of get a sense of what they do in Quebec, kind of thing. And it's been a very busy week, and I can't remember exactly. Yeah, I'm getting them all mixed up. I know I spent a lot of my work in BC, and I know in BC, and as well, I'm becoming more and more familiar with the Ontario regulations. They explicitly talk about stream temperature as a management concern. I'm pretty sure, and Sylvain and I came to the same conclusion. That's not that. You're absolutely right. That's not the case in Quebec. I think it's a happy consequence of their regulations, but nowhere is water temperature, stream temperature, river temperature explicitly mentioned in the Quebec regulations for this sort of stuff, which is kind of interesting. But yeah, hope that kind of answers your question. But thanks. Yeah.
Thank you, Jason. Est-ce qu'on a d'autres questions orales dans l'audience? Des questions écrites?
There's a question from Jan about what cheese it was, and I've got it written down in my I've got a picture of it on my phone and written down somewhere, but I can't. Is this one that's wrapped in spruce bark and can't. Yeah, Miss Sylvain will put it down. Yeah, adoré. Yeah, yeah. God, that tastes so good. I miss it so much. That was, yeah, unbelievable. What a cheese.
It's the adoré from Fromagerie Montebello. So along the way to get to Sault Ste. Marie, driving there. So.
Oh, I think we've got another Sibel.
Yes.
Hi. So you heard me? You're hearing me? Okay. I didn't quite understand finally. So is there a buffer for your clear cut around the river?
Effectively, no.
Okay.
They weren't. There was no.
Okay.
Short answer. Yeah.
Okay, but so do you think if there was a buffer, the temperature water would be less higher, or?
Yeah, from a like a from a very sort of simple, like, first principles, of course, like if you left sort of more trees over these streams, you would likely get more shade. I do think, like, there's a couple of factors with these really small streams, and as I sort of mentioned, these streams dry out during the summer very often, and so in those cases, it really doesn't matter what vegetation is there. If there's no water, it's not going to warm. The other thing too is that these are small streams, and I know from other work that has shown for really sort of narrow buffer strips, you can get a lot of sort of sunlight coming in sort of on an angle or sort of almost laterally through the sort of the understory area or the lower portion of the thing that can actually still drive sort of a decent amount of warming, especially at sort of more northern latitudes where we have generally lower solar angles, even during the sort of the peak of the summer kind of thing. So the flip side with that is that these small streams, that understory vegetation that regrows after you remove most of the canopy can actually provide a lot of effective shade in a short period, compared to a larger river system where you really need those mature trees to provide sort of extensive a shading effect kind of thing. So anyway, yeah, there's a bunch of just blabbing. Yeah.
And so so the amount of water into the river affect the temperature when there's and did you see a difference between the streams where there was a clear cut or another cut, like between the amount of water between the clear cut? Was there less water in the streams where it was a clear cut?
Yeah, no, that's an excellent point. So some of this work was published by Jim Buttle, who's a hydrologist at Trent, or he recently retired hydrologist at Trent University, who looked before I arrived at the CFS, looked at some of these stream flow responses. And so, yeah, in short, the strongest sort of stream flow response was at the clear cut site, and the shelter and selection cuts were a bit more modest in terms of their responses. There is a complicating thing where I believe it was the selection harvest seemed to show a stronger streamflow response than the shelter would. And that's very likely attributed, and Sylvain will love this story, to the one of the access roads that they built into the watershed. It's very likely that it was diverting a lot of flow into the stream, and may have caused a greater sort of increase in flow there. But your comment, I think, is really interesting, and kind of gets back to something I didn't mention earlier about that sort of the clear cut site and the potential sort of an open question in sort of how harvesting affects stream temperature is this idea of you may have a riparian buffer strip, but if your soils and your shallow surface waters are being heated in the clear cut area, and then that water is transported and evected into the stream, you may see a stream temperature increase that is really driven by that energy exchange instead of for the radiative heating at the stream surface itself. This is something that's been speculated, I feel like, for a while now in the sort of the forest harvesting stream temperature literature, but we don't have a lot of detailed work or empirical work done on answering that question specifically. But anyway, your comment, maybe you're going there with your questioning, but your comment reminded me that's kind of a neat little sort of thing to consider with some of this stuff. But...
All right, thank you.
Thank you. Yeah.
Merci beaucoup, Cybèle. Est-ce qu'on aura d'autres questions orales ou écrites? On va patienter un peu. Je pense qu'on n'a pas d'autres questions. Et comme il n'y a pas de questions, j'aimerais clôturer ce webinaire. J'aimerais remercier beaucoup Jason pour cette excellente présentation. The Forest Water Nexus in a Changing Environment, 40 plus years of insight from the Turkey Lakes Watershed. En terminant, je vous invite au prochain colloque qui aura lieu dans 2 semaines, le 8 février 2024, et qui s'intitule Technologie et données en conservation, expérience de conservation de la nature Canada. La conférencière sera Madame Marie-Michelle Rousseau-Claire, chef de la conservation à Conservation de la nature Canada. Je vous invite également à surveiller notre fil Twitter et LinkedIn pour en savoir plus. Donc, je vous remercie beaucoup de votre participation et bon après-midi.
Merci beaucoup. Bye.
Join as guest, je pense que je suis connecté.
Il y a du monde,
Il y a un monsieur, là, l'host,
qui
Fahed El Ferrani. Je